Are you experiencing joint pain? Is this joint pain limiting your ability to go about your daily life? Well, look no further, because I have the solution for you. Galtherian is an anti-inflammatory ointment made with methyl salicylate to help you go back to your daily activities. Methyl salicylate is the product of salicylic acid and methanol. In reality, the reaction doesn't go to completion. It's at something we call equilibrium. In other words, we need to work up our crude product in order to get our pure product. If you stick around, we'll give you the scientific breakdown of how Galtherian goes from crude product to anti-inflammatory product. Hi, my name is Taylor, and I'm here to take you through the scientific breakdown. Stay tuned. To begin the formation of methyl salicylate, we added methanol, solid salicylic acid, and sulfuric acid. But wait, sulfuric acid isn't in the final equation for the formation of methyl salicylate, so why is it there? Let's take this back to the lab and let one of our experts, Parisa, explain this one.
Sulfuric acid is used in the synthesis of methyl salicylate as an acid catalyst. Since sulfuric acid is a very strong acid, pKa -3, it completely dissociates into hydronium ions and its conjugate base, hydrogen sulfate. If you look at the slow step of the reaction when it's catalyzed, you can see that the proton reacts with the salicylic acid, forming a charged reactant. Compared to the uncatalyzed slow step, salicylic acid remains neutral. The presence of a charge on the reactant increases the ordering effect on water, so the catalyst basically makes the reactant more unstable. Now, if you look at the products of the catalyzed slow step, we only have a positive charge on the product, whereas in the uncatalyzed slow step, we have a negative charge and a positive charge. So the catalyst stabilizes the products and destabilizes the reactants. So overall, delta H will become less positive. It's still positive because we break a stronger C double bond O and form a weaker CO bond. Lowering delta H makes the slow step more energetically favorable.
We let the reaction stir without heat addition for 15 minutes, and then run the reaction on reflux for another 30. So what's the reasoning there?
So overall, we determined that our catalyzed reaction is exothermic and the slow step itself is exothermic. And the reason why is we looked at the mechanism and we just broke it down step by step. So if you look at the first step, basically you're just forming an OH bond, so that's going to be exothermic. And in the second step, this is a slow step, and you're basically breaking a C double bond O and forming two CO bonds. So delta H is going to be negative, it's going to be exothermic. In the third reaction, you have an acid-base reaction, and you're breaking and forming an OH bond. So if you look at bond enthalpies, overall delta H would be 0. So then we looked at the strength of the acid and base. So if we were to compare these two acids, this is acid and this is the conjugate acid. Basically, this acid has the ability, basically has a bunch of electron withdrawing groups around it. So it allows the delocalization of charge, of this positive charge in oxygen, compared to this guy. So we said this acid is stronger, thus product favored, and thus exothermic, we said. And fourth step is also endothermic, we thought. So we saw that we're also breaking and forming an OH, but if you look at the strength of the acids and bases, this base, again, has those electron withdrawing groups, so it makes it a weaker base. So overall, we would favor the reactants, thus making it endothermic. The fifth step, it was simple. It was basically kind of like the opposite of the second step. We're breaking two CO bonds and forming C double bond O, so it's going to be endothermic. And the last step, acid-base reaction, we were breaking and forming OH bonds. So we looked at the strength of acids and bases. So this acid versus this conjugate acid here, in this acid, you have the potential to form resonance structures, whereas this conjugate acid cannot. So we said this is a stronger acid, thus making it product favored and exothermic. So overall, if you look at each of the steps, you have mostly product favored or exothermic. So we said we believe overall the catalyzed reaction is exothermic. Running the reaction on reflux means that we are running the reaction at higher temperature. And when temperatures increase, the number of collisions of the forward and reverse reactions of our catalyzed slow step increases as well. Since the forward reaction of the slow step is bimolecular, increasing the temperature would have a larger impact compared to the reverse, as a collision is required for the product to form. Therefore, there's going to be more products formed when you increase the temperature. However, since our reaction is exothermic, the extent of the reaction is going to decrease because increasing the temperature makes the entropic factor more dominant, and we determined that our catalyzed reaction is entropically unfavored. That means that extent favors the reactants. In short, reflux allows us to produce methyl salicylate at a faster rate while sacrificing extent.
After removing the now crude product of methyl salicylate and water from the reflux contraption, we can add that to the centrifuge tube, along with sodium bicarbonate and dichloromethane, which we don't have in the studio right now. But sodium bicarbonate and dichloromethane serve as our aqueous layer and organic layer, respectively, so that we can commence with the pH extraction process.
Methyl salicylate is more soluble in dichloromethane because of the high surface area nonpolar benzene ring. Therefore, it will remain in our organic layer, forming dispersion forces. On the other hand, water exhibits hydrogen bonding and therefore is more likely to interact with the polar aqueous sodium bicarbonate, as shown here. let's not forget about our catalyst. Since sulfuric acid is dissociated into its ion forms, the positive and negative charges will interact with the positive and negative charges associated with the sodium bicarbonate. The remaining salicylic acid should also go into the aqueous layer because the two opportunities for hydrogen bonding dominate the large benzene ring's dispersion forces. After allowing the solution to settle, we performed a sodium bicarbonate wash. The reason we do this is so we can get salicylic acid to react with sodium bicarbonate to create a soluble salt and be more soluble in the aqueous layer.
After extracting the aqueous layer, we added yet another round of sodium bicarbonate to create a sodium bicarbonate wash. So why would we do that?
So if you look at the reaction of when we add sodium bicarbonate, basically sodium bicarbonate is reacting with the salicylic acid to form salicylic salt, CO2, and H2O. And the reason we incorporated a second sodium bicarbonate wash because it shifts this reaction to the right. By removing the aqueous layer, we decrease the concentration of the salicylic salt and add more sodium bicarbonate, both of which shift the reaction to the right because it makes Q less than K. And in order to reestablish equilibrium, we have to make the reaction make more products. And so we can remove salicylic acid from the organic layer because the salt is strongly soluble in the aqueous layer. So in general, we do a second wash to make sure we remove all impurities.
To complete the pH extraction process, we extracted, the key word in the procedure, the aqueous layer from the workspace in a centrifuge. To confirm that the pH extraction was successful, we tested the pH of the aqueous layer to confirm that it was the higher pH that we wanted.
When pH is greater than pKa, there's going to be more of the deprotonated form than the protonated. And when pH is less than pKa, we're going to have more of the protonated form compared to the deprotonated form. And this all has to do with our selected pH value and environment it is in. So we wanted to use a pH of 8 for two reasons. One, the pKa of salicylic acid is 2.97, so increasing the pH will deprotonate salicylic acid and make it more prone to interact with the polar aqueous layer, removing it from the organic layer. And at the same time, we wanted to keep the pH below 9.8 because methyl salicylate is predominant in its neutral form between a pH of 3 to about 9.8. So you can see here the graph, this is where the change is occurring. And so we chose 8, for example, and not 5 because we wanted to ensure that we had an abundance of neutral methyl salicylate so we could extract it.
Last step, we took our organic layer and heated it up so we could evaporate the dichloromethane out of the system because dichloromethane has a boiling point at 40 degrees Celsius. This works because methyl salicylate, our desired product, has a boiling point at 222 degrees Celsius. To confirm that our certified plan was truly certified, we had our team of scientists run a couple of confirmation tests to make sure that our methyl salicylate was in its pure form. First, let's have a look at HNMR. Well, it's missing a few things. Although it has the methyl group of 3.88 ppm, hints of the aromatic ring hydrogens ranging from 6 to 8 ppm, and a small peak correlating to the OH bond at 11 ppm. Each peak is slightly diluted by the dichloromethane peak at 5.3 ppm. This is an implication of not having enough pure neutral product in the NMR2, meaning that our pH could have exceeded 9.8, which is the parameter for neutral methyl salicylate before it is deprotonated. Any other issues are beyond my education as an infomercial provider. Let's have Parisa explain our second method of verification, GCMS.
After looking past the fluctuating spectra, we see that our yielded crude product has a 28% purity of methyl salicylate. According to the second mass spectrum, we can see that it correlates to methyl salicylate. As we can see here on this diagram, the benzene ring plus the OH group sums to the 92 mass per charge ratio, and the entire molecule, excluding the 1 hydroxyl group, correlates to the 120 mass per charge ratio, and the 150 is the entire molecule. Our product yield was 21%. This was determined by dividing a variable by the total mass of our pure product, 1.0 grams, and equaling that to our purity. After finding that value to be 0.28, we divided that value by our ideal mass of methyl salicylate, 1.133 grams, to get our quotient of 21%. Therefore, there is a 72% impurity in our product. Our team of scientists came to the conclusion that our sources of error were caused by high concentration of dichloromethane and smaller hints of our reactants.
Now that you know the chemical basis of how we make Galthurian, you can truly appreciate the beauty of not having inflamed joints. Because you so avidly listened to our infomercial, we are giving you a limited time offer. If you buy one bottle of Galthurian, we'll throw in another one for free. Just call 520-164-0001 and say give Taylor and Parisa an A, and we will send them right over to you with no shipping fee. You can find Galthurian not at your local drugstore due to our pending FDA approval. Some side effects of Galthurian include redness, burning, stinging, blistering, and swelling. This may be fatal if swallowed, so if used or ingested in high concentrations, please visit your local hospital. Pure methyl salicylate has equal strength to many aspirin. We also recommend that you keep your supply of Galthurian away from children under the age of 12 to keep them from inappropriately using our product. Galthurian. Inhale the wintergreen, exhale the happiness.